So when I pick up my calculator, it's 5.55 divided by 110.98 and then times 2. Again, many AP chemistry students would forget to multiply by 2. So when I do this math, I get 0.100 moles of chloride ions. Now be careful. The correct answer to question 3 is not choice C. We're not done yet. We have a number of moles, but we do not have the moles per liter. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 3.7 to 3.10. As you can see on this slide, these topics fall under Unit 3 in the AP Chemistry curriculum, Properties of Substances and Mixtures. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 3.7, Solutions and Mixtures. Here are some essential knowledge statements from the AP Chemistry course and exam description. Solutions, also sometimes called homogeneous mixtures, can be solids, liquids, or gases. In a solution, the macroscopic properties do not vary throughout the sample. In a heterogeneous mixture, the macroscopic properties depend on location in the mixture. Solution composition can be expressed in a variety of ways. Molarity is the most common method used in the laboratory, and the equation for molarity is molarity, abbreviated with a capital M, is equal to the moles of solute divided by the liters of the solution. Here you can see what the first page or the front page of the AP Chemistry equations and constant sheet looks like. So this would be the section where the definition or the formula for molarity can be found, the section entitled Gases, Liquids, and Solutions. And at the top, you can see that the metric prefixes are listed, and I'm highlighting milli, so you probably already know this, and that is that 1 liter is equal to 1,000 milliliters, so that's relevant for solution calculations. So there's the highlighted equation. Molarity is equal to the number of moles of the solute divided by the liters of the solution. Now let's move on to the practice for topic 3.7. This is question 1. In question 1, it says, information about 4 different aqueous solutions is shown above. Based on this information, which solution contains the greatest mass of solute? So on the equation sheet, another equation that is located in that same section relates to molar mass. So the number of moles of a substance is equal to the mass divided by the molar mass. So in question 1, we will take the volume and convert that to moles. I'm just showing you that the volume in liters times the molarity, which is moles per liter, will give you the number of moles. And then if we keep going all the way to grams, then the number of moles times the molar mass, which has units of grams per mole, will give us the mass in grams. So putting those two relationships together, let's begin with choice A. We have 100 milliliters, so I'll start with that number. First, I'm going to convert from milliliters to liters, and that would involve that relationship that I had mentioned earlier. So there's 1,000 milliliters in 1 liter. Now I'm going to use the molarity. It says 0.70 capital M, and then Ki, or potassium iodide, is the formula for the solute. So there's 0.70 moles of potassium iodide for every 1 liter. And then I don't have to go to the periodic table and calculate the molar mass of Ki because that information is already listed in the table. So the molar mass of potassium iodide is 166 grams per mole. So when I pick up my calculator, from left to right, that would be 100 divided by 1,000 times 0.70 and then times 166, I get approximately 11.6 grams for the mass of solute. Now I'm going to move on to choices B, C, and D, and then we will eventually use the same procedure for choices B, C, and D. So starting with choice B, 250 milliliters. This is my conversion to go from milliliters to liters. Then I'm going to use the 0.50, and that's capital M for molarity. So 0.50 moles of potassium chloride, KCl, for every 1 liter. And again, they're giving us the molar mass of each substance, so there are 74.6 grams of potassium chloride for every 1 mole. So from left to right, 250 divided by 1,000 times 0.50 times 74.6, and the number of grams of solute works out to be approximately 9.3 grams of potassium chloride. Well, since in question 1, we are looking for the solution that contains the greatest mass of solute, I know that the correct answer cannot be choice B because 9.3 is less than 11.6. Now moving on to choice C, 500 milliliters, convert from volume to liters, 0.20 capital M, that's 0.20 moles of sodium iodide, or NaI, for every 1 liter, and then times 149.9 grams of sodium iodide for every 1 mole. So 500 divided by 1,000 times 0.20 times 149.9, and I get almost exactly 15 grams. So since 15 grams is larger than 11.6, I can eliminate choice A. So now it comes down to choice D. We have 1 liter, or 1,000 milliliters, 0.20 moles of sodium chloride, NaCl, per liter, and then I'll finish it up with the molar mass, 58.4 grams of sodium chloride per mole. So obviously 1,000 divided by 1,000 is 1 times 0.2 times 58.4. I get about 11.7 grams of sodium chloride. So which of these 4 solutions contains the greatest mass of solute? The winner, the largest mass, would be choice C, 15 grams. So hopefully that makes sense, and you should feel comfortable using molarity as a conversion factor, whether you're going from moles to grams, grams to moles, volume to grams, etc. So let's go ahead and take a look at question 2. In question 2, we are given a data table. It says solution 1 and solution 2. We are given the mass and the identity of the solute and the volume of solution. And question 2 says, information about 2 different aqueous solutions is listed in the table above. Which solution has the greater electrical conductivity and why? So we have KOH, which is known as potassium hydroxide, and we have CH3OH, which is known as methanol or methyl alcohol. So the fact that potassium is a metal and that OH is actually the hydroxide ion, potassium hydroxide, when dissolved in water, will split up into potassium ions and hydroxide ions. So potassium hydroxide, or solution 1, is a good conductor of electricity. Now, you might be thinking, does CH3OH split up into ions in the same way? And the answer is no. So there's the Lewis diagram of CH3OH. When that carbon is bonded to oxygen, that is not going to break up into ions such as CH3 plus and OH minus. So CH3 plus is not a common polyatomic cation or positive ion. So just like sugar, when dissolved in water, will remain as molecules, alcohols such as methanol and ethanol and isopropyl alcohol have a carbon bonded to an oxygen and then bonded to a hydrogen, but they remain as molecules. They do not conduct electricity. So we have a substance solution 1 contains potassium hydroxide, which does contain aqueous ions. And then we have a different substance, solution 2. As molecules, it does not conduct electricity. Now let's go ahead and take a look at the 4 choices for question 2. So we know that solution 1 conducts electricity and solution 2 does not conduct electricity. So the correct answer to question 2 is either choice A or B. And it turns out it's because potassium hydroxide, or KOH, completely dissociates in water to produce aqueous ions. That is the better explanation for electrical conductivity. Now, choice B was not a good explanation of conductivity. It just talks about how the number of moles of KOH is greater. That's not a good explanation. It's also not even true. I did the math to calculate the number of moles of KOH, and it was actually less than the number of moles of CH3OH. So a substance that breaks up into aqueous ions is a good conductor of electricity. Now let's take a look at question 3. In question 3, it says a solution is prepared by dissolving 5.55 grams of CaCl2 solid, that's calcium chloride, into water. And the total volume of the calcium chloride solution is 500.0 milliliters. The concentration of the chloride ion, Cl-, in the solution is, and we have 4 numerical choices, and the units are molarity, or moles per liter. Now, just like potassium hydroxide in question 2 was an ionic substance that splits up into separate ions when dissolved in water, calcium chloride is also an ionic substance. So you should know that the charge on the calcium ion is 2+, and the charge on the chloride ion is minus. So we have calcium chloride splitting up into separate ions. Now, we are given 5.55 grams, and we are given 4 choices that talk about molarity, or moles per liter. So a good first step is to convert that 5.55 grams of calcium chloride into moles. So on the periodic table, I did the math. I looked up the atomic mass of calcium and chlorine, and the molar mass of CaCl2 is 110.98 grams. Now, this next step in my conversion factor and my calculation is probably a step that some AP chemistry students would forget to do. So the next step is to actually convert moles of calcium chloride into moles of chloride ions. Hopefully you can see that there are 2 moles of chloride ions produced for every 1 mole of calcium chloride, CaCl2. So when I pick up my calculator, it's 5.55 divided by 110.98 and then times 2. Again, many AP chemistry students would forget to multiply by 2. So when I do this math, I get 0.100 moles of chloride ions. Now be careful. The correct answer to question 3 is not choice C. We're not done yet. We have a number of moles, but we do not have the moles per liter. Remember that there are 1,000 milliliters in 1 liter, so that means that 500 milliliters of solution would correspond to half a liter. So 0.100 moles of chloride ions is dissolved in a total volume of half a liter. So what's the molarity, or the concentration of the chloride ion in units of moles per liter? It would be 0.100 moles of chloride ions divided by 0.5 liters. Now, when you do that math, you do get the correct answer, which is not choice C, it's actually choice D. But most likely, a student that forgot to multiply by 2 would have picked choice C, and that would have been incorrect. All right, let's go ahead and move on to question 4 in the packet. This is not a multiple choice question. This is a free response question. Now, if you're watching this video, I assume that you are preparing to take the AP Chemistry exam, and you should know that a free response question can involve both calculations and written descriptions or explanations. So with calculations, always show your work and be very clear in the setup for your calculations, especially with units. And then for written descriptions or explanations, make sure that you are also very clear with your word choice, with your language, and your use of proper vocabulary and terminology. So we're going to see calculations in parts A and B of this question, and then in part C, we'll see a written description of a laboratory procedure. So in question 4, it says, a student needs to prepare a solution of aluminum nitrate, which has the chemical formula Al and then NO3, or nitrate in parentheses, times 3. And in part A, it says, calculate the concentration of the nitrate ion, NO3 minus, in a solution of 1.20 molar aluminum nitrate. So the molarity of the aluminum nitrate is 1.20. That's 1.20 moles of aluminum nitrate per liter. So at first glance, you might think, well, we already have a concentration. It's 1.20 molar. So what's the concentration of the nitrate ion? Well, just like potassium hydroxide in question 2, and just like calcium chloride in question 3, aluminum nitrate is an example of an ionic compound. So watch what happens when aluminum nitrate breaks up into ions. For every 1 mole of aluminum nitrate, we actually get 3 moles of nitrate ions. So all you really need to do to answer part A of question 4 is take that 1.20 molar and multiply by 3. But let's be very clear with how we show our work. If you just write 3.60 molar and no work, you would not get credit for this answer. So this is me showing that 1.20 moles of aluminum nitrate for every 1 liter, and now I'm multiplying by 3. There are 3 moles of nitrate ions for every 1 mole of aluminum nitrate. So 1.20 times 3, my answer to part A, and I'm showing my work, is 3.60 moles per liter. Now let's move on to part B, and part B is actually a dilution or a dilution. So a dilution is when you start with a solution of higher concentration, and then you add water to produce a solution of lower concentration. So how can we tell that this is a dilution? It says, calculate the volume of 1.20 molar aluminum nitrate that is needed to prepare 50.00 milliliters of, and again, there's that lower concentration, 0.480 molar aluminum nitrate. So we're starting with a solution of higher concentration, we're adding water, and we're diluting it to produce a lower concentration. So I'm going to begin with the volume of the diluted solution. So that's 50.00 milliliters. Next, I'm going to convert from milliliters to liters, and the reason why is because molarity is moles per liter, and I want the liters to cancel out. So 50.00 milliliters times 1 liter over 1,000 milliliters. Now, here comes that 0.480 moles of aluminum nitrate for every 1 liter. Now, if I stop right now, that would be the number of moles of aluminum nitrate. But I have to connect that to the original solution, which has a higher concentration. So watch what happens next. I'm going to take the molarity of the higher concentration, and I'm going to write it upside down. So now I've canceled out the moles, and you might say, wait, now we're back at liters again. Let me go ahead and convert that to milliliters, which will mean that the first conversion factor is going to be upside down. So let me go ahead and summarize. I went from 50 milliliters to liters. Then I used the 0.480 moles per liter as a conversion factor. Then I used the other solution of higher concentration. I went from moles to liters, and then finally back to milliliters. Now I'm going to give you another way of solving this problem, but this is the correct answer to the question if I start with 50 divided by 1,000 times 0.480 divided by 1.20 and then times 1,000. This is what I get on my calculator. Now, if you're thinking, is there an easier way to solve this problem? And the answer is yes, but I'll go ahead and teach you that this is something I had presented in my video for topic 3.7. So this is called the dilution equation in my video for topic 3.7. I have molarity times volume equals molarity times volume. So on the left, we have a more concentrated solution. That's a darker shade of blue in this example. And on the right, we have a more diluted solution of a lighter shade of blue or a lower concentration. So M times V equals M times V, where we have the concentrated solution on the left and the diluted solution on the right. Note that these two volume amounts could either be in liters or milliliters. As long as you have the same units on both sides of the equation for volume, then you will get the same answer. So we know that the correct answer to part B is 20 milliliters, but here is that M times V equals M times V equation. So the molarity of the more concentrated solution would be 1.20 molar. The volume of the concentrated solution is actually, we don't know yet. I'll just put a question mark. But then the diluted solution has a concentration of 0.480 molar, and we know that the volume of that diluted solution is 50 milliliters. So how do we get our answer? Let's solve for the volume of the concentrated solution, and that would be 0.480 times 50 divided by 1.2. And when you do that math on your calculator, you also get the same answer, which is 20 milliliters. So if you like that M times V equals M times V dilution equation, again, I had presented that in my video for topic 3.7, so feel free to check out that video for more examples. Now, let's move on to part C of this question. This is where you have to write the description of the laboratory procedure. So it says in part C, briefly describe the procedure that the student should follow to prepare 50 milliliters of 0.480 molar aluminum nitrate using that stock solution of 1.20 molar aluminum nitrate. Now, as far as the procedure, it says the following laboratory equipment is available for the student to use, and assume that all appropriate safety precautions will be taken. So we have distilled water for the dilution. We have the stock solution of 1.20 molar aluminum nitrate. We have an electronic balance, although we don't really need that. And then we have 3 different pieces of glassware. We have a 50 milliliter beaker, we have a 50 milliliter graduated cylinder, and we have a 50.00 milliliter volumetric flask. We also have a plastic dropper pipette. Now on this next slide, this also comes from my video that includes topic 3.7. There is a procedure for preparing a solution, performing a dilution. So you have to first do the calculation to determine what volume of stock solution is needed. We've already done that in part B of this question. That was the 20 milliliters. Use a graduated cylinder. You can also use other types of glassware for measuring volume, such as a burette or a volumetric pipette. So measure the volume of the stock solution, and then you choose the appropriate volumetric flask. Transfer the measured amount of stock solution to the volumetric flask. Fill the volumetric flask with distilled water until you get to the calibration mark on the neck of the flask. Seal the flask and mix the final solution to ensure that it's homogeneous. So again, check out my video for topic 3.7, and I go through procedures for preparing solutions. All right, the first thing I'm going to write in my description of the procedure in part C is the fact that we already got the volume in part B, so I will mention use the graduated cylinder, not the beaker. The graduated cylinder is more precise, to measure out 20 milliliters of that stock solution, the 1.20 molar aluminum nitrate. Now we have to prepare this in a volumetric flask. So transfer the 20 milliliters of solution to a 50 milliliter volumetric flask. So that is the piece of glassware we use for preparing solutions. Then we're going to be adding water. So dilute the solution with distilled water. Use the dropper pipette to add water carefully near the end so that the bottom of the meniscus is even with that calibration mark on the neck of the volumetric flask. And then finally seal the flask and mix the final solution to ensure that it's homogeneous. All right, well, that was the end of question 4, which was the last practice question for topic 3.7. Now let's move on to the review for topic 3.8, representations of solutions. So here is an essential knowledge statement from the AP Chemistry course and exam description. Particulate representations of solutions communicate the structure and properties of solutions by illustration of the relative concentrations of the components in the solution and/or drawings that show interactions among the components. And now let's move on to the practice for topic 3.8. This is question 5. In question 5, it says, a student dissolves a small amount of solid magnesium bromide in water. Then the student draws the particulate diagram shown below to represent the ions present in the magnesium bromide solution. Water molecules are also included in the student's drawing. So we can see in the drawing we have water molecules, which are represented by a gray circle. That's the oxygen atom in the water molecule. And there's 2 white circles touching that gray circle. Those are the hydrogen atoms in the water molecule. Then we have a black circle representing the magnesium ion, and we have a white circle, a larger white circle representing the bromide ion. So here is question 5, part A. It says, which ion or ions in this particulate diagram are surrounded by water molecules with the correct orientation around the ion? Answer by drawing a circle around one of the choices below. So I'm referring to what are known as ion dipole forces in this diagram. And this would be back from topic 3.1, intermolecular and interparticle forces. It's an example of an attractive force between ions and polar molecules. Now, in my video for topic 3.1, when I was talking about ion dipole forces, I had presented this question. So I have a sodium ion on the left, and I have a chloride ion on the right. So there's the sodium ion surrounded by 3 water molecules, and there's the chloride ion surrounded by 3 water molecules. Now look carefully at the orientation of the water molecules around each ion. So it turns out that since oxygen is more electronegative than hydrogen, then that polar HO bond, or that polar water molecule, does contain a partial negative charge and a partial positive charge. So because oxygen is more electronegative than hydrogen, the oxygen atom carries a partial negative charge, and the hydrogen atoms carry a partial positive charge. So the partial positive charge on the hydrogen atoms are directed toward that negative chloride ion, but then the water molecules have been reversed around the sodium ion, where the partial negative charge of the oxygen atom is directed toward the positive sodium ion. Now, back to question 5, you can see that I'm circling with these red circles in the diagram the orientations that are correct. So around that magnesium ion, the water molecules have their positive end pointing toward the positive magnesium ion. That's incorrect. But around the negative bromide ion, the water molecules have their positive end oriented toward the negative bromide ion, which is correct. So now to answer part A, only the bromide ions have the correct orientation of the surrounding water molecules. And then in part B of this question, it says, justify your selection in part A by identifying the partial charges on the hydrogen atoms in a polar water molecule. So again, based on differences in electronegativity between hydrogen and oxygen, the partial negative charge is on the oxygen atom, and the hydrogen atoms in the water molecule have a partial positive charge. So the answer to part A of question 5 is that only the bromide ions have the correct orientation of the surrounding water molecules, and the justification in part B is that the hydrogen atoms have a partial positive charge. All right, there's one more part of question 5, and that is part C. It says, does this particulate diagram show the correct ratio of magnesium ions and bromide ions that are present in a solution of magnesium bromide? If your answer is yes, justify your answer, but it turns out that the answer to part C is no. So if your answer is no, explain what the correct ratio of magnesium ions and bromide ions should be in this particulate diagram. So we need charge balance. Okay, we need charge balance in this diagram, and since magnesium is positive 2 and bromide is negative 1, then the ratio cannot be what you can see in this diagram is a 1-to-1 ratio. That's incorrect. It should be a 2-to-1 ratio, 2 bromides for every 1 magnesium. So the answer to part C is no. And the ratio should be 1 magnesium 2 plus ion for every 2 Br minus or bromide ions. And this is necessary for the charge on the ions to be balanced. All right, well, that's the last part of question 5. We have another particulate representation of solutions. Now let's take a look at question 6. In question 6, it says the diagram above shows a 1 molar solution of potassium nitrate with a particulate diagram that represents a highly magnified view of a representative sample of the solution. Note that water molecules are not shown in the magnified view. And the diagram also shows a 2 molar solution of calcium nitrate. Which of the following diagrams most accurately represents the magnified view of a 2 molar solution of calcium nitrate? Note that all magnified views represent the same volume of solution. Now, just like I talked about in part C of question 5, we need charge balance in these particulate diagrams. So when I say we need charge balance, if we have K plus and NO3 minus, that would be a 1-to-1 ratio to get charge balance for those ions. But since calcium is +2 and nitrate is -1, then the ratio should be 1 calcium ion for every 2 nitrate ions. Let's consider the 4 choices in question 6 and see if we see that proper 1-to-2 ratio. Now in choice A, it's a 1-to-1 ratio of ions, so I'm going to eliminate choice A. And then in choice C, I also see a 1-to-1 ratio of ions, which I know is incorrect, so I can eliminate choice C. So I know that the correct answer to question 6 is either choice B or choice D because it shows 1 calcium ion for every 2 nitrate ions. There's one more detail we need to focus on, and that is the concentration is not the same in each beaker. So in the beaker on the left, it's a 1 molar solution, but then the beaker on the right, it is a 2 molar solution. So what does twice as concentrated mean for this particulate diagram? Well, instead of 2 gray circles representing 2 potassium ions, it needs to be twice as concentrated, so there should be 4 gray circles in the diagram. And that means that the correct answer to question 6 is choice D. So with a twice as concentrated solution, that means double the number of positive ions. It's going to be 4 calcium ions, and then based on that 1-to-2 ratio, there should be 8 nitrate ions. So the correct answer to question 6 is choice D. Now let's move on to the review for topic 3.9, separation of solutions and mixtures. Here are some essential knowledge statements from the AP Chemistry course and exam description. The components of a liquid solution cannot be separated by filtration. They can, however, be separated using processes that take advantage of differences in the intermolecular interactions of the components. So we have chromatography, paper, thin layer, and column, separates chemical species by taking advantage of the differential strength of intermolecular interactions between and among the components of the solution, the mobile phase, and with the surface components of the stationary phase. And the resulting chromatogram can be used to infer the relative polarities of components in a mixture. And we also have distillation. Distillation separates chemical species by taking advantage of the differential strength of intermolecular interactions between and among the components and the effects of these interactions have on the vapor pressures of the components in the mixture. So now let's move on to the practice for topic 3.9. This is question 7, which has to do with chromatography. It says, a chemist sets up an experiment to separate a mixture of 2 substances labeled as J and Q using column chromatography. The chemist adds the mixture of J and Q to the top of a column filled with silica gel, a polar material. The column is filled with a nonpolar solvent that flows downward through the column. And during the experiment, the chemist observes the separation of the components of the mixture as shown in the diagram at right. So we can see that downward flow of the mobile phase, that non-polar solvent. And then we can see that substance Q is traveling a greater distance through the column. It's moving more quickly. And substance J is traveling a shorter distance and is moving more slowly. Now here comes the question. Which of the following identifies the substance that has the stronger attraction for the stationary phase in this experiment and provides a valid justification? So the stationary phase, so not the mobile phase, the stationary phase. The stationary phase doesn't move, so if a substance in the mixture has a strong attraction to the stationary phase, then it will travel a shorter distance through the column, and so that would be substance J. Substance Q is moving very quickly through the column, but substance J is not moving very quickly, so substance J must be more strongly attracted to the stationary phase. So we know that the correct answer to question 7 is substance J, so I'm going to go ahead and eliminate choices C and D. Is it because substance J is less polar or more polar than substance Q? Well, it says that silica gel, which is the stationary phase, is a polar material. So substance J, if it is attracted to this polar stationary phase, it is likely that substance J is the more polar component. So as we will see in topic 3.10, polar substances tend to be attracted to other polar substances, and then non-polar substances tend to be attracted to other non-polar substances. So if substance J is attracted to this polar stationary phase, then we can predict that substance J is the more polar component in this mixture. So the correct answer to question 7 is that in choice B, substance J has a stronger attraction for the stationary phase, and it must be more polar than substance Q. Now let's move on to question 8, which is about distillation. So we have 2 molecules shown above, and it says the structural formulas of 1-propanol and 1-octanol are shown above. A mixture containing equimolar amounts of 1-propanol and 1-octanol is separated using distillation. So based on the diagrams shown above, which of the following identifies the substance in the mixture that would be initially present in a higher concentration in the distillate and provides a valid justification? So the first thing I'm going to do is show you something I had mentioned in my video for topic 3.1, specifically about London dispersion forces. So the strength of the London dispersion forces increases as the number of electrons in an atom or a molecule increases. And we can definitely see a different size of the electron cloud for 1-propanol and 1-octanol. So the larger the electron cloud is, the more likely that it is that the electron cloud can be distorted or polarized. In other words, the larger the electron cloud is, the more polarizable it is, and the stronger the London dispersion forces between the particles. So comparing the relative strength of the attractive forces between the particles helps us to make predictions about boiling points. And again, with distillation, it's all about the relative strength of the attractive forces and the boiling points. So the boiling point of a substance is related to the relative strength of the attractive forces between the particles. So we have a smaller electron cloud on the left, which is the 1-propanol molecule. And then we have a much larger electron cloud on the right, the 1-octanol molecule. Now, although each molecule can experience London dispersion forces, and they're polar, that would be dipole-dipole forces, as well as hydrogen bonding, because the hydrogen directly bonded to the oxygen atom, they can experience all 3 of these intermolecular attractive forces. The significant difference between 1-propanol and 1-octanol is the size of the electron cloud. So I'm going to focus on the difference in the relative strength based on the London dispersion forces. So a larger electron cloud, stronger London dispersion forces for 1-octanol, smaller electron cloud, weaker London dispersion forces for 1-propanol. So we have a lower boiling point for 1-propanol and a higher boiling point for 1-octanol. But we haven't answered that question about the distillate. So in my video for topic 3.9, this is what I had said about the distillate. The diagram above shows the setup for a distillation experiment. Distillation is used to separate the components of a mixture that have different boiling points. The mixture is heated gently until the component with the lowest boiling point begins to boil. The vapor rises up through the glassware and reaches the condenser, which is the portion of the apparatus that is surrounded by cool water. The vapor condenses into a liquid and is collected in a separate container. So here's the part about the distillate. The liquid that is produced in a distillation experiment is known as the distillate, and the component of the mixture that appears first in the distillate is the one with the lowest boiling point. So in question 8, we are looking for the substance with the lower boiling point, and that would be the 1-propanol. So the correct answer for question 8 is choice A. The substance in the mixture that would be initially present in a higher concentration in the distillate is going to be 1-propanol because it has weaker London dispersion forces and therefore a lower boiling point. All right, well, those two questions, question 7 and question 8, were examples of practice for topic 3.9. Now let's move on to the review for topic 3.10, solubility. Here we have a very brief essential knowledge statement from the AP Chemistry course and exam description. Substances with similar intermolecular interactions tend to be miscible or soluble in one another. All right, now let's move on to the practice for topic 3.10. This is question 9. In question 9, it says, the Lewis diagram of hexane, C6H14, is shown above. Which of the following molecules is most likely to be soluble in hexane? So what I'm looking for would be a similarity in the polarity of the two substances that should form a favorable attraction with each other. So what I don't want is that one is polar and one is nonpolar. What I'm looking for is that both substances are polar or both substances are nonpolar. And with respect to the polarity, I'm looking for symmetry or asymmetry. So if the bond dipoles in the molecule cancel one another out, the molecule is nonpolar. And that's what I see for C6H14 for hexane. There's a lot of symmetry in C6H14. All of the bond dipoles cancel one another out. So hexane is classified as nonpolar. So what I'm looking for is another nonpolar molecule to form favorable attractions with molecules of hexane. As you already know, water, which is a bent molecule, is polar. So the bond dipoles in the molecule do not cancel one another out. So water is polar, but CCl4 in choice B looks very symmetrical, and those bond dipoles do cancel one another out. So I would classify CCl4 based on the symmetry as nonpolar. That makes most likely choice B the correct answer for question 9. Let's go ahead and take a look at the polarity of the molecules in choices C and D. I don't see perfect symmetry for the molecules in choice C or in choice D. So those bond dipoles for the molecules in choices C and D, they will not cancel each other out. So the molecule in choice C is polar. The molecule in choice D is also polar. So the correct answer to question 9 is B, CCl4, which is a symmetrical molecule, is classified as nonpolar. And so when two substances are both nonpolar, they are likely to form a solution and mix well with each other. All right, let's take a look at question 10, which is also about the polarity and solubility. In question 10, it says, the structural formulas of two different compounds are shown above. Which of the following choices identifies the compound that is more soluble in water and identifies the strongest type of attractive forces that are formed between the molecules of the compound and molecules of water? Now, you already know that water is polar, so we are looking for a polar substance to form strong attractive forces with water molecules. Hopefully you can see that compound 1 is very symmetrical. All of the bond dipoles would cancel each other out. So compound 1 is classified as nonpolar. It's looking like compound 2 is going to be polar, but you might not see that based on that structure. So you might think that the OH group on the left is going to be canceled out by the OH group on the right. Let me show you a different arrangement of compound 2. So there's compound 1, very symmetrical and nonpolar, and now maybe you can see a better representation of compound 2. Compound 2 is polar, and here is a water molecule. Not only is compound 2 polar, it can form a hydrogen bonding attraction with a nearby water molecule. So the correct answer to question 10 is going to be compound 2, and we're going to focus on hydrogen bonding attractions. So again, which of the following choices identifies the compound that is more soluble in water? So compound 2, and then what's the strongest type of attractive forces that are formed between molecules of the compound and molecules of water? Again, that hydrogen bonding interaction. So it's going to be choice D, compound 2, and hydrogen bonding attractions between molecules of compound 2 and molecules of water. All right, well, that was the answer to question 10. Now we have come to the part of the lesson where I give you advice to help you avoid common mistakes. So the first thing that I'm going to mention is I do have a YouTube playlist that's organized by AP Chemistry CED units. So for topics 3.7 and 3.8, you can review the information in that particular video, and there's the link. And then for topics 3.9 and 3.10, you can review the information in that other video, and again, there's the link. I will mention what I normally mention during this part of the lesson, and that is read the question carefully and make sure you are answering the question that is being asked. Now, avoid the use of vague language with words such as it. Be specific with your word choice and strive to use the proper terminology in your responses. This is especially true when you refer to particles or the attractions between them. So there is a difference between atoms, molecules, and ions. There's a difference between chemical bonds and interparticle attractions. So it's also important to be clear and precise with your language when you write the steps of a laboratory procedure, as we saw in question 4 of this lesson. My next piece of advice is to be careful to avoid the following common mistakes with molarity calculations, and we see this very frequently on the AP Chemistry exam. So students make mistakes with the following: incorrect unit conversions when converting from milliliters to liters or vice versa, incorrect unit conversions when converting from grams to moles or vice versa. Students have a failure to show units in the setup for their calculation, which can increase the risk of making calculation errors or algebra errors. And then students, they might have the correct answer to the question. Now, failure to show any work can cost you points on the AP Chemistry exam. You must show your work to receive credit for your answer. My next piece of advice is to practice making standard solutions in the laboratory using volumetric flasks and other laboratory equipment. Be familiar with the two common procedures for preparing a standard solution. You can start by dissolving a solid solute in water using a volumetric flask, or you can also begin with a stock solution and perform a dilution, as we saw in question 4 in this lesson. My next piece of advice for you has to do with particle diagrams. So practice working with particle diagrams, both writing them and interpreting them in questions related to solutions, and focus on the following details: the proper orientation of the water molecules around the aqueous ions, the proper ratio of the ions in the particle diagram based on the chemical formula of the ionic compound and the overall balance of the charges on the ions, the proper spacing between the ions based on solid compounds versus aqueous solutions. So for example, the ions in the solid should be packed close together in a crystal lattice, whereas the aqueous ions should have empty space around each ion. And sometimes water molecules are not included in a particle diagram, so you might have to have that empty space. Otherwise, if there are water molecules, then again, the proper orientation of the water molecules around the aqueous ions. And then finally, as we saw with potassium hydroxide versus methanol, pay attention to the difference between non-electrolytes, such as methanol, that do not break up into ions, versus electrolytes, such as potassium hydroxide, that do break up into ions in solution. My next piece of advice has to do with chromatography. So, with respect to chromatography, be familiar with the following details. With paper chromatography, the mobile phase, or the solvent, flows through the paper from bottom to top. But with column chromatography, the mobile phase flows from the top of the column to the bottom. The substance in the mixture that has a stronger attraction for the stationary phase will travel more slowly, or travel a smaller distance. And on the other hand, the substance in the mixture that has a stronger attraction for the mobile phase, or the solvent, will travel more quickly, or travel a greater distance. Now, if the mobile phase is polar, then the substance in the mixture that is more polar will travel a greater distance. And if the mobile phase is nonpolar, then the substance that is less polar will travel a greater distance. My next piece of advice is about distillation. So with respect to distillation, be familiar with the following details. Distillation can be used to separate homogeneous mixtures of solutions of two different molecular substances that have different boiling points. And the substance that experiences weaker intermolecular attractive forces should have the higher vapor pressure and the lower boiling point. This will be the substance that is initially present in a higher concentration in the distillate. And then the substance that experiences stronger intermolecular attractive forces should have the lower vapor pressure and the higher boiling point. My next piece of advice is about using careful word choice. So do not use words such as bonds or bonding to describe the attractive forces between the solute particles and the solvent particles. Now, I know that there is hydrogen bonding attractions, but when you just say bonding or bonds, then the readers think you're talking about chemical bonds. Now, the process of forming a mixture or a solution between two molecular substances does not normally involve breaking or forming of chemical bonds, so be careful with your word choice. When providing an explanation for why a certain solute is soluble in a certain solvent, identify the specific type of attractive forces between the solute and the solvent, such as London dispersion forces, dipole-dipole forces, hydrogen bonding attractions, or ion dipole forces. And if you were to write the following response to explain why the solubility between two substances is favored, this explanation would not earn the point. If you say, quote, both molecules are polar, so like dissolves like, that would be an incorrect explanation and would not earn the point. Remember that a solution is a mixture of two different substances. So when you identify the attractive forces in a solution, talk about the attractions between the solute particles and the solvent particles. Be careful that you don't describe the attractive forces within the sample of a pure substance as opposed to a mixture or a solution. Now, these last 4 points on this slide are very relevant to the 2022 free response question number 4, part B. And the links to the relevant documents for the 2022 free response questions are included in the video description area. So question 4, part B was focusing on two compounds. We have NH2Cl on the left, and we have NCl3 on the right. You can see the Lewis diagrams for each molecule. So part B of question 4 said, NH2Cl is highly soluble in water, whereas NCl3 is nearly insoluble. Explain this observation in terms of the types and relative strengths of the intermolecular forces between each of the solutes and water. Now look at those last few words there. Between each of the solutes and water. So not within molecules of NH2Cl as a pure substance, it's about the solute and the solvent, and the solvent is water. So what I'm going to show you is a hydrogen bonding attractive force between a water molecule and a molecule of NH2Cl. I can do the same thing with the molecule of NCl3. So you might think that NCl3 cannot form hydrogen bonding attractions, but with that lone pair, that nitrogen atom, the lone pair on the nitrogen atom, that can be a hydrogen bond acceptor. So there's the water molecule forming a hydrogen bond attraction to NCl3. That was surprising for some students that that was possible. So I've got more sites on the NH2Cl molecule that can form hydrogen bonding attractions with a nearby water molecule. Now I'm going to show you the official scoring guidelines for question 4, part B from the 2022 AP Chemistry exam. So this was a 2-point explanation. So first, you get 1 point for the correct identification of intermolecular forces between each substance and water, and they accepted either hydrogen bonding attractions or dipole-dipole attractions. And then you also had to say that the intermolecular forces between NH2Cl molecules and water are stronger than those between NCl3 molecules and water. So it had to do with the greater number of hydrogen bonding sites on the NH2Cl molecule. So now what I'm going to show you is from the Chief Reader Report. I've highlighted responses that demonstrate understanding in green, and then you'll see when I switch from green to red that I show you examples of student mistakes. So what did students do well on this question? Well, if they clearly differentiated between chemical bonds and intermolecular forces, that was good. They talked about intermolecular hydrogen bonds with water, that the hydrogen atom bonded to the nitrogen atom in the NH2Cl molecule can form a hydrogen bond with the oxygen atom in the water. So there's an example of a hydrogen bonding attraction between NCl3 and water, but that's only one spot, whereas with NH2Cl, it can form more hydrogen bonds with water, which explains its higher solubility. Hopefully that helps you understand the difference between NH2Cl and how it interacts with water and NCl3. So we have weaker attractions with NCl3 and water, and we have stronger attractions between NH2Cl and water. Again, students did well to show that when NH2Cl dissolves, we have these hydrogen bonds that are formed between the solute and the solvent. And now, these are the common misconceptions or mistakes that students made. So a common error was that students did not clearly differentiate between bonds and intermolecular forces. So again, be careful with your word choice. They said NH2Cl has hydrogen bonds. It sounds like they're talking about the bonds within the molecule and not attractions to other water molecules. So watch out for your word choice. Another common error was not focusing on the difference in the number of hydrogen bonding sites. And they would say things like, well, they're both polar, so like dissolves like. Again, that would not earn the point. Students did not recognize that the non-bonding pair of electrons on the nitrogen atom in NCl3 can participate in hydrogen bonding with a water molecule. A third common error by students was incorrectly stating that these chemical bonds were broken or that ions were formed. So again, watch out for your careful word choice, especially when you're talking about things like bonds or the identity of the particles. Finally, students would often fail to address the prompt by not focusing on the interactions between each solute and water. They would simply discuss the type of intermolecular forces between the solutes, or they discuss the intermolecular forces in a pure sample of the solute and not the interactions between the solute and the water. So again, this was a good example of common mistakes This was the 2022 exam, question 4, part B. So the summary in the Chief Reader Report for the 2022 exam was to give the following advice. Again, many responses indicated that NH2Cl has hydrogen bonding. That was a mistake. A much clearer response would be to indicate that NH2Cl can form hydrogen bonds between its molecules in water. Describe the attractive intermolecular force between a solute molecule and a water molecule as a hydrogen bonding interaction. Try to avoid the just bond. It sounds like you're talking about chemical bonds when you do that. So say hydrogen bond attraction or interaction. The H atom covalently bonded to the nitrogen atom in NH2Cl can form a hydrogen bond with the O atom in water. That's very clear on the between molecules approach. Talk about hydrogen bonding in terms of hydrogen bond acceptors, such as that lone pair on the nitrogen atom, and hydrogen bond donors, such as the hydrogen directly bonded to the O in the water molecule. So NCl3 is a hydrogen bond acceptor. However, NCl3 cannot be a hydrogen bond donor because it doesn't contain hydrogen atoms. So again, be very clear with your language. During the solution discussion, mention that hydrogen bonding interactions can occur when one of the molecules engaged in the interaction does not form hydrogen bonds in its pure state, such as NCl3. It cannot form hydrogen bonds within itself, but it can form hydrogen bonds with water molecules. So the nitrogen atom in NCl3 does have a lone pair of electrons, and it can serve as a hydrogen bond acceptor. All right, well, hopefully all of that advice from the 2022 AP Chemistry exam, question 4, part B, was helpful, talking about solutions and careful word choice and language. So now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 3.11 to 3.13. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.